Hey guys, so for this video, I'm going to be going over structural isomers, cis-strand isomers, constitutional isomers, which are the same thing as structural, and just talk about those and give some examples to what this is. And then I'll be going over one example of this problem that's seen on the exams, and we'll show you how to do that as well. Okay, so to start off, we need to talk about what exactly is an isomer. Okay, so an isomer is a molecule or molecules that have the same structural formula, but they may not necessarily have the same connectivity or the same configuration or the same optical, optical arrangement. Okay, but what's important is that they have the same number of atoms as each other. They may not necessarily be the same visually, or the way that they're connected, but they have the same number of atoms as each other. So let's just look at the worksheet. Okay, so for the worksheet, let's look at number 1. So for number 1, we have, well, the worksheet says give the relationship between the following paired structures. Blah blah. You have different options. You have same compound, cis-trans isomers, constitutional isomers, and they're not isomers at all. So different molecular formula. The first one, I have CH3, CH2, CH2, CH3, and CH3, CH. Now, at first glance, these might seem like they're not isomers, right? But the first thing that we can do, because it's not blatantly obvious, we can count the number of atoms. So I have 3 hydrogens, 2 hydrogens, 2 hydrogens, 2 hydrogens. So that's 5 and 5. I have 10 hydrogens. So I'm just going to put H10. And I have 1, 2, 3, 4 carbons. So I have C4, H10. And over here I have 3 carbons and 1 other carbon here. So I have C4. And I have 3 times 3, that's 9 hydrogens plus 1. So I have H10. So these molecules have the same, right, molecular formula. They have the same molecular formula. So they can be isomers. They're not completely different compounds. If they're completely different compounds, they had, 5 carbons and one of them had 4 carbons, I can't compare them at that point. So now that I know they have the same formula and I can they're an isomer, they're isomers of each other. Okay, now I need to see, what kind. So it helps to draw. So I have, this is just a straight chain of carbons. So what this looks like is 1, 2, 3, 4. That's what this one looks like, right? This one over here is 3 carbons, right? 3 CH3, so I have 1 CH3 over here. I have another one over here. I have another one over here. Okay? Connected to a CH. Right? Right. I did that wrong. Back. Right, connect to a CH. So I have 1 CH3, 1 CH3, 1 CH3. This is the carbon. It has hydrogen right here. Okay? So this is the other one. So so what would you say that the relationship between these molecules are? They have the same molecular formula, but they have different connectivity, right? So this one would be, right? This would be structural, right? So they're structurally different connectivity. All right, moving on to the next one. So when we look at constitutional isomers, we usually are dealing with double bonds and the way that atoms are arranged around those double bonds. And double bonds are unlike single bonds. And one thing I should probably introduce first is that single bonds, so sigma bonds, have free rotation around their joints, right? So these bonds over here, they're able to move around, okay? But around double bonds, pi bonds, I am fixated. The atoms around these are fixated there, so they can't move. So they're stuck like this. So if I have it like this, I have a double bond and I have things coming off of here. This is stuck this way, this is stuck this way. Okay, I can't keep flipping. This won't come up here unless the whole molecule itself flips. Okay, so these don't move around as normally as something like this would, right? If I had connectivity like this around these carbons over here, these groups are constantly moving around, right? Constantly moving. But around double bonds, these groups are fixated. So that's a big difference. So for number two, the first thing to check is, do I actually have um, the same chemical formulas? So I have three carbons. I have two hydrogens, another hydrogen, so that's 3, 4, 5. And then I have one chlorine, right? I have 1, 2, 3 carbons. I have 1, 2, 3, 4, 5. Okay, and I have one chlorine. Okay, so they are the same. So these are isomers. They are isomers now. Okay, so now I need to determine they're cis-trans isomers, right? Constitutional isomers. So that's the structural. And then if they're not isomers whatsoever, so we've already determined that they are isomers. And whether they are the actual same compound, just flipped in a different way in space. Okay, so a cis-trans isomer is, for example, let's say I had this double bond, I had hydrogens, right? And I had a CH3 group, CH3 group. So what you do over here is, when you have two of the same group coming off a double bond but on opposite sides, so this top side is one side, right? This top side is one side, bottom side, okay? So when I have the same group, this allows me to add a label to this double bond, okay? That lets me differentiate it and give me some information about it. So I have two methyl groups that are coming off of this double bond over here. A methyl group is just a CH3. Okay, so because they're on opposite sides, we call this trans. But if the double bond was drawn like this, the hydrogens, I'm gonna leave them invisible. This is called cis. Okay, and it happens when I have two comparable groups of the same type of groups on the same side. Okay, so in the beginning they were on opposite sides, now they are both on the same side, right? And the hydrogens are also on the same side. So that's cis, this is trans. And then when we have cis-trans isomers, these are isomers that are just on different orientation on the double bond, but they are essentially the same almost. They have different characteristics. Right, so this is what we're trying to determine. Are these cis-trans isomers, or are they something else? So over here, the best way is to look at where the double bond is. So I have a double bond between a CH2 and a CH. CH2. So this one looks like this. The first one looks like this. So I'm going to draw my double bond, and then I have two hydrogens coming off of this carbon right here. This is what this one looks like. And then on this one, I have a hydrogen, right? And I don't know whether this one's up or down. I'm just drawing it according to how I see fit, right? So I have a CH2Cl coming off over here. This one looks like this. Okay, so I have off of this carbon right here, I have an H and a Cl. And then off of this carbon right here, I have an H and a CH3. There's a reason why they don't draw it out like this, because what we're going to see is that these are not cis-trans isomers, okay? They are constitutional or structural isomers. And as you can see that they have the same molecular formula, but the connectivity is different. Off of one double bond, I have a CH2Cl group. Do I see this group repeated over here? I don't, right? I have the Cl off it by itself. I have the CH3 off by itself. I have these H's off by itself. It's different. It's different. So these are also This is also structural. Okay, number 2 is structural. All right, clean some of this up. Okay. All right, number 3. So number 3, let's look at it. All right, now they've drawn it out with us. They've drawn out the double bonds for us, and it's very clear that we could see if it's cis or trans or structural or constitutional, right? So I have a double bond. I have 2 CH3 groups coming off. Do I have to go through the effort of counting the number of things? Is it pretty clearly visible that I have the same number of things? I have a CH3 group, and I have a double bond with hydrogens, double bond with hydrogens. Right, so let me just draw these hydrogens out. All right, so like I said, we're going to compare essentially the same thing that I just did, actually. Okay, so the CH3 groups are on the same side, and everything else is the same connectivity, right? The same type of groups coming off of the double bond, rather than over here I had different groups. So I see that these are on the same side, so this is the cis version. This is the trans version. The CH3 groups are on opposite sides. So this is number 3 is a cis-trans isomer. Okay? Now for number 4, I have a double bond. I have a CH3 group coming off here, CH3 group coming off here. Now I have a double bond. I have a CH2 over here on this side, so hydrogens, and I have CH3, CH3. Okay, so let's just count the number of things. I have 1 carbon over here, 1 carbon over here, 1 carbon over here, 1 carbon over here. So I have C4. Right? I have 3 hydrogens, that's 6, 7, 8. Okay? C4H8. All right? 1, 2, 3, 4 carbons. All right? 6 hydrogens plus 2, so that's 8. So yes, they are isomers. They have the same molecular formula. But now what are they? Are they cis-trans or are they structural? Well, if we see over here, this is completely different bonding, right? No matter whether this was, whether the hydrogens, because this is what this looks like. Okay, hydrogens are out like this, and then I have my methyls, right? This is what this looks like. No matter whether or not that, nothing's gonna change how this looks, right? There's no way to change it. This one doesn't even have its own sister trans. Like this, hydrogens are always gonna be. There's always gonna be one hydrogen on the top. There's always gonna be a hydrogen on the bottom, no matter what. It's not gonna. You're never gonna get 2 of the same groups on the same side because of the way the connectivity is over here. So this one has completely different connectivity. On the bottom, I have 2 hydrogens. On the bottom over here, I have a carbon, I have a CH3 group, and a hydrogen. So it's very different connectivity, and they're not sister trans versions of each other. So this is structural. Okay, number 5. So another double bond. So the best way to look at this is just to draw out your hydrogens, right? They're always invisible. And then I'm gonna look at where the double bond is. So first thing first, let's just make sure that it's the same. So I have 1 carbon group, 2, it's 3, 4, 5, 6, 7, 1, 2, 3, 4, 5. Alright, so messed up, but let's just count again. So I have 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay, so on both of these I have 7 carbons, I have a CH3 group, and everything else is just along the chain. So I have the same formula. Okay, so now I need to just draw out my hydrogens. I need to compare them, right? So on this one, I have a hydrogen going down. I have 2 carbons going up. So I have hydrogens going down, 2 carbons going up. Okay, and then over here I have a CH3 going up, and I have the 2 carbon group going down. So what I'm interested in is looking at whether or not I have anything different. I have a hydrogen and the 2 carbon group on the same side. right? So over here, on this one, I have, right? Yes. Okay, so I have the hydrogen and this group on the same side, right? So on this one, I have these groups are on opposite sides, and on this one, these are on the same side. Okay? Now, the way that we need to do this is you have to find two groups that are the same, and then that lets us, you know, that's what we use to compare the two molecules. So I have to find two groups on the molecule that are the same, and then see where they are relative to each other on the molecule. So this one, they're on opposite sides of the double bond, and on this one, they're on the same side. Okay, so this is a cis trans, right? This one is the trans, this one is the cis. Okay, moving on. Right, let's get the rest of them. All right, so this is the rest of them. All right, for number 6, we have this straight chain, so it's 1, 2, 3, 4, 5 carbons long. This one's 1, 2, 3, 4, 5 carbons long. They're the exact same, right? I have just a straight chain of 5 carbons. This is a straight chain of 5 carbons. Yeah, they're drawn differently, but they can be drawn in any way, right? So like I said, you have, these are all sigma bonds, right? These are all sigma bonds. Sigma bonds can freely rotate, so I can go like this, I can go like this, whatever. They're moving around, they're bending, right? So these are all the same molecule. So this is the same compound, right? And I just realized I put the answers up here, but it's fine. So for this one over here, number 7, I have so I have this molecule, right? And I have this one. Now they look like they're different, right? They have the same molecular formula, right? For sure. It's the same thing, just the double bond is in a different place, seemingly, right? So what we do to compare this, we're going to look at what's bonded to this double bond, right? So on this one, I have the hydrogens going up, okay, right? And I have the hydrogens going up over here, and then I have the chain groups going down. And then over here, I have the chain groups going in opposite directions, and I have the hydrogens on opposite sides as well. Okay, so this one, the chain groups are both going down, and for this one, chain groups are going in opposite directions, they're on opposite sides. So this is the trans version, this is the cis version, and this is the cis trans molecule. Okay, and then number 8, it's pretty easy. So I have a double bond, and then I have this double bond O group, right? So over here I have these hydrogens, but over here, even though I have the same molecular formula, right? But my connectivity is different, right? So 1 carbon away, I have this double bond O. 2 carbons away, on the second carbon, I have the double bond O. So right away, you can see that, I can't compare these in terms of cis or trans. These are straight up, they're structural. Okay? All right. And let's keep going. And here are the rest of them. Okay. So number 9. For number 9, what do we have? So we have the same molecular formulas over here. So I have a Br, a Br, a Br, a Br, and then I have 4 hydrogens, and 2 carbons. So it's the same. Okay. So now we need to determine, do we have structural? Do we have cis-trans? Do we have, are they not even isomers? So we determine they are isomers, they're the same formula. Are they the same compound, right? So I don't have a double bond here, so that's not cis-trans, okay? Now I need to see if the connectivity is different. Is the connectivity different? Well, seemingly it looks like the connectivity is different. But like I said, these are all sigma bonds, and sigma bonds are always rotating. So I need to see if I can achieve this connectivity or not. So if I rotate this Br up, right, this H up over here, and this H down over here, right, it's like a steering wheel. I just turn it, right, and I just move them all, these three bonds that are coming off the carbon, these three groups coming off the carbon. If I just, turn it like a wheel, right, so I bring this Br over here, this H over here, this H down here, what do I get? So if I bring the H down here, I have that H over there. If I bring the Br over here, I have that over here, and I have this H over here, and then, I have whatever, right? I want to see if I can get this shape. If I do it one more time, if I bring the H down, this over here, and the Br over here, okay, on this carbon, I'll have the Br like this. The carbon bond is over there still. This H comes down, and this H is over here. Does this look like this? Yes, it does, right? So, these are the same compound, okay? It's just free rotation that's making it look seemingly different, all right? So now we have the next one. So on the next one, we have two double bonds, but they're not, the BRs are both on different sides, right? The same molecular formula, right? It's clear to see. They're on the different sides, but it's flipped. One is over here, and this one is over here. Okay, so these are the same, right? And like I said, these bonds can't move, but what can move is the actual molecule itself. So if this whole molecule flips in space upside down, we will achieve this molecule, right? And one way that you can see this is if you just just kind of imagine I flip it like a pancake. So when you flip it, this group is going to go up here, this group's going to go down here, this group's going to come down here, this group's going to go over here. So that's, if you flip it along the line, right, this line over here, all you're doing when you're flipping it, you're just bringing this group up, this group down, this group up, this group down. And then when you do that, it looks exactly the same, okay? So these are the same molecule. For number 11, right, it's another one of these types of problems. So I need to look at this first thing. I want to make sure I have the same formula, right? So CH3 group, and I have 4 hydrogens, 1, 2, 3, 4 hydrogens and 2 carbons. So they are the same formula. So now I need to look at, can I achieve, so this side is the same as this side. It's only this side that's different. So can I achieve, right? Can I achieve this side if I rotate? So if I bring this one up here, right? This one over here, and this one down here. Rotate it like a wheel. You can rotate it in any direction, okay? Just as long as you rotate them all the same way, all in the same direction, clockwise or counterclockwise. I'm bringing this CH group over here, so that will give me that over there. This H will come down here like this, and then this H will go up here like this. So they are the same. All right, and for this one, now it's very similar to the other problem, right? The double bond is connected to the ring, and a CH3 group, and a hydrogen. This double bond is connected to the ring, but 2 hydrogens. So, very clear that these are structural, right? Different connectivity. That's what structural means, okay? So that's that for the worksheet problems. And now I want to look at a test problem that will be more like what you guys have to do. Okay, so this is a type of exam problem that you will see. All right, so this is what the instructions will say. It says, draw all the structural isomers resulting from the monobromination of the compound shown below. And I'm going to draw the compound for you guys. The compound is this one, right? So draw up here, nice. Actually, I'm going to draw up the line thing. Let's see, right? That. Okay. All right. And now I need to go back to the pencil, and then over here on this one, I have to like that. All right. So she says, draw the structural isomers resulting from the monobromination. So she says structural isomers, right? What are structural isomers? Structural isomers when I have the same, right, same molecular formula, but I have different connectivity, right? So I have some groups are connected in different places than when I'm comparing different molecules of these isomers. Okay, so just different connectivity. That's what that means. And then the next confusing thing is monobromination. So what the hell is monobromination? Bromination is when you have a bromine and I am adding it to a molecule. So you have other things. So mono, so I'm adding mono, right? Mono means one. So I'm adding one bromine to this molecule, right? You have other versions of this called monochlorination. So you're adding a chlorine, mono, whatever. It's usually one of these two, monobromination, monochlorination, okay? She just tries to trip you up with fancy language that she hasn't used before, and she's just making sure it's kind of it tricks people, but it's just one way to throw you off. But it's not actually that hard. So monobromination. So I'm adding a Br to this molecule, and where am I? And that's kind of it makes sense, right? Because if she just gave you this and nothing else to work with, you can't make isomers from this unless you broke these bonds and you're just moving them around. But what she wants you to do is she wants you to brominate this molecule once, and she wants you to give as many isomers, structural isomers of this bromine attached to this molecule as possible. So as many different locations. Okay? So let's do that. All right? So before I add my bromine, right? The first thing that you need to do when you're doing isomer problems is you need to kind of figure out the environments, right? How many different environments do I have? And what that means is how many actual different carbons do I have on this molecule before I start repeating myself. So this molecule is, as you can see, I have 1, 2, 3, and then the fourth one right here that has these things coming off, then 1, 2, 3. So you can say this molecule is symmetric around this point, okay? This line over here. So that means on this side of the molecule is exactly the same as this side of the molecule. So anything, if I do, anything on this side that's going to be done is going to be the same thing if I do it again on this side. So I'll be repeating myself if I did it on the other side. Okay, so that's what that means. So I have this CH3 group, I'm going to call it A, right? It's unique, right? I have a CH3 group. This is a CH2 group. This is another CH2 group. Oh, that's not B. This is C, right? So all unique. And then I have this carbon over here. And what I want to look at, right, when I'm doing bromination, what it requires to brominate is not just to attach a carbon, obviously, but that carbon has to have a free hydrogen, right? So it has to have at least one hydrogen for the bromine to attach to that location, right? So ignore this line, but I have this carbon over here, and I have 1, 2, 3, 4 carbons coming off it. So this middle carbon right here has no hydrogen. So I am not going to look at that environment, this carbon right here. So I'm going to ignore it. I can't do anything with it. Now I have these carbons up here. So this carbon right here is a CH3 group, and it's unique, so I'm going to call it D, right? So I've labeled everything on this half, and I'm just going to label everything on this half. So this is D because these are symmetric. So doing something to this D is the same thing as if I did over here, right? And this is the same over here. So this is C, this is B, this is A. I hope everyone can see what I'm doing. So this is an example from her exam. All right, so this is an example from her exam. I need to just draw it again. Okay, so I redrew it. Sorry for the technical difficulties, but so over here, this is the molecule, and I've redrawn it. And so this A is the same as this A because the molecule is symmetric. So now what I'm going to do, I'm going to start brominating along these points. So I have 4 unique environments, so that means I have 4 unique places where I can brominate and I don't repeat myself in the molecules that I draw. So I'm going to start brominating. All right, let's do site A first. So site A, I'm going to attach a bromine over here. Okay, so that's 1. Okay, so now I need to do site B. Attach a bromine over here. Now I need to do site C. I think you get the point. So I need to attach a bromine over here. And now I need to do site D. And I attach a bromine over here. And what I've been saying is if I attached a bromine, let's look at this one for the site B attachment. If I drew this molecule, okay? And I said, and I put this on my answer and I'd be like, yeah, this is another unique isomer. But actually these two are the same molecule. They're just flipped in space. So if I flipped this one, right? If I flipped it in this direction, right? And I kind of flipped it over to put the right side on the left side and the left side on the right side, I'd get this same molecule over here. Okay? So that's why we need to make note of all the symmetric environments and just make sure these are all the same. So if I have symmetric environments, then I will be repeating myself if I put the bromine on this other side. Okay, so that's just the important part. So this is not a valid structure. So these have 4 isomers that are structurally different. All right, so that's it for isomers really, and that's all you need to know how to do. I'm not sure if there's another version of this poem, but if there is, we'll talk about it in lecture, okay, in workshop. All right, see you guys in the next video.